Welcome to the Insightful Professor. Having addressed the general issues of structure for user-defined types in a relational framework, we now turn our attention to the subject of identity. We'll see that identity has assumed various forms, being addressed in different ways depending upon the environment being considered. What we mean is that identity within a programming language is accomplished in a different way than identity is achieved within a database. And if we consider an object-oriented system versus a relational system, we'll see additional differences. So furthermore, the identity within a database may depend upon the particular model that's being followed, whether it be the hierarchic model or relational model or object-oriented model. Remember that our concern lies within the evolution of a relational system in order to incorporate complex data or objects or user-defined types. So we'll discuss some general issues or concerns and then focus on the approach that's used specifically within the Oracle database management system to support the definition of new types. A database is a representation of the real world, some subset of the world that we refer to as an application domain. Typically, when we develop a model of the real world, we're using a technique such as an entity relationship diagram or an entity relationship model. So we come up with representations of entities that exist in our application domain. To be faithful to their real-world counterparts, these representations must provide some way to distinguish individual instances. Talking about the entity relationship modeling approach, we define an entity as something that is uniquely identifiable or distinguishable within that application domain. So the concept then of identity comes into play. Identity is that property of an object which distinguishes each object from all others. This is a definition that comes from a paper presented by Koshafian and Copeland at a conference in 1986. The authors note that identity has been addressed in programming languages and in database languages. They indicate that these investigations have been independent of one another. What this means is that different approaches have been taken due to the different agendas. The authors also stress the importance of identity as these two different environments tend to evolve and merge together due to the incorporation of object orientation within a database system. Note that in addition to the identity of individuals, a database management system must also be concerned with capturing relationships between these individuals. The approaches taken by a relational database management system and an object-oriented database management system with respect to both identity and relationships are quite different. In a relational framework, we talk about relations and tuples. Less formally, we talk about tables and rows. In a relational database management system, identification can be considered to be value-based, using a primary key. The value of one or more attributes of a tuple, one or more columns from a table, serve to distinguish that tuple or row from other tuples or rows within the relation or table. Furthermore, unless we are using a surrogate key, the attribute or attributes of the primary key have semantic value. That is, they have some meaning to a user acquainted with the application domain and the entity represented by that relation. While this might seem obvious, it is an important point that we shall examine when we consider objects and object support within a database management system. So what observations can we make? A primary key ensures uniqueness but only within the table or relation for which it's been defined. It does not have the broad scope of encompassing the entire database. A primary key could possibly be changed. Its value could be changed depending upon what we call the relational update rule. An update rule refers to whether you are permitted to modify the primary key of a parent row when there are children or child rows making a reference to this parent row. Most systems impose a constraint and simply say, on update, restrict. You're not allowed to update the primary key if there are child rows making a reference to it. And finally, a primary key is accessible to users. It is something that effectively relates to a component within the real world that users are acquainted with. So therefore, we don't make any effort to conceal the primary key. It's actually something exposed and accessible to users. Again, the exception would be if this primary key was a surrogate key. Then it wouldn't have any meaning to users, although they should have access to it. In an object-oriented database management system, the system employs something called an object identifier, or an OID. An OID has no meaning within the application domain. It's a mechanism employed by the database management system to ensure uniqueness of object instances. As such, there are different characteristics for this means of identity. The identifier of an object must be immutable. What that means is it cannot be altered in any way. The correspondence between an object and its identity in the form of an OID effectively cannot be altered. It persists for the lifespan of the object. The OID is system generated. Again, it has no meaning within the application domain. It's used exclusively within the object-oriented database management system to establish that uniqueness. An object's identity persists until the object is destroyed, again for the lifespan of the object. An object's identity is unique within the entire system. Each object has its own identity, even if all of the properties of two different objects are identical. Two objects have the exact same values for all of their attributes. They can still be distinguished from one another based upon the object identifier that each possesses. The object identifier should not be accessible to users. It has no meaning or relevance to them. It's a mechanism used by the system. We could also use keys. Keys can be used with objects as a set of properties that uniquely identify an object within a collection. The uniqueness is guaranteed only within the collection in which the objects reside, not across the entire system. Within a hybrid object-relational database management system, we see things a little bit different. An ORDBMS supports the representation of an object either as a column or an attribute or a tuple or a row. Stored within a column, we refer to this as a column object. Stored within an entire row, we refer to this as a row object. Row objects are stored within what are called object tables or typed tables. Column objects are stored within relational tables. Because a column object is embedded in a row of a relational table, a column object does not have an object identifier. When you reference a column that holds an object type, you retrieve the whole object. To access a column object, you need to access the row that contains that object. This row provides the relevant context for that embedded object. Thus, we can consider column objects to be identified by the primary key of the containing row. So a column object is part of a tuple in a relation, and as such has meaning only within the context of the tuple. The tuple is identifiable through other attributes, the concept of the primary key. A row object, on the other hand, is assigned a system-generated OID. Thus, if an object is to exist in its own right, it should be instantiated as a row object in an object table or a typed table. If an object's existence is strictly dependent upon some other entity, the object can be instantiated as a column object. So a column object cannot be shared. Access to such an object is achieved only through access to the row in which the object resides. That is, the row provides a context which gives meaning to the column object. We'll see that Oracle database supports two types of OID. The system-generated OID that I suggested here, but also a form of an OID that's based on the primary key of the table. Again, I'm referring to an object-relational database management system as kind of a hybrid system. It's no longer purely relational, nor does it achieve pure object-oriented behavior or characteristics. Now we turn our attention specifically to features or characteristics of Oracle database to continue our case study. System-generated OIDs are the default for row objects in an object table. An object is assigned a unique object identifier which requires 16 bytes of storage. The objects are automatically indexed for efficient OID-based lookups. So there's a performance factor here in terms of how Oracle has implemented this. Additionally, Oracle database supports up to 2 to the 128th power, 2 to the 128 object identifiers based upon the length of an object identifier. The OID is automatically assigned when an object is stored as a row object. The OID is stored within a hidden column of an object table. It's not intended for users to access this because it really has no meaning or relevance to them. So Oracle does not really provide direct access to the internal structure of the object identifiers because this is something that could change over time. Oracle could change the way they represent the OID. But the OID does serve an important purpose. It's used by the Oracle system to construct references to row objects. So the OID can be referenced from columns in other tables using what's called a ref type modifier that represents the reference to an object. So effectively, the ref is a combination of the OID and some metadata for that object table, plus something that Oracle uses in its relational framework called the row ID, which effectively is like the physical location of the record within the database system. But again, applications are only concerned with using object references for fetching and navigating among objects. There should be no concern for the details of how an OID is represented. A ref is a built-in data type that holds an object identifier. It forms the basis for capturing relationships that involve objects. It's a logical pointer or reference that's derived from an object ID, gives us access to row objects. A ref can be used to access a row object, can be used to obtain that object, examine it, or update the row object. Through a ref, we have a legitimate or legal access to the OID. Remember, the OID is effectively concealed or hidden from a user. It's not intended for users to access it directly. But through a ref, we gain access to the object whose identity has been stored within the ref. Because a ref is a reference to an object, it can be changed to point to a different object of the same object type hierarchy. A ref can be used like a foreign key to identify a related object. Where we had indicated the ref forms the basis for capturing relationships involving objects, this is what we're talking about. A row object can be referenced from other objects. A row object can be referenced from a relational table. And what this means then is we can see a ref as an attribute of one kind of object that allows us to relate to or connect to another type of object, forming complex structures. A ref could also be the data type of a column within a relational table where we wish to refer to a row object stored in an object table. The language of SQL has a ref operator, which allows the retrieval of this pointer from an object table. When using this ref operator, the ref operator accepts as an argument a correlation variable that refers to that object or typed table. As we continue our discussion, we'll be presenting examples to bring all of these ideas together and to further illustrate these concepts. So an object identified by a ref potentially could become unavailable. Maybe the object that was being pointed to has been deleted or removed from the database. Or access to the object has been changed in terms of a privilege that was required to access the object having been revoked from the user. The user no longer has the authority to examine the object, to follow the pointer. In such cases, the ref is no longer usable because it doesn't effectively point to anything. This is called a dangling ref. Oracle Database provides an SQL predicate called isDangling to test refs for this specific situation. And we'll provide examples and a further discussion of this point a little bit later. When we wish to follow this logical pointer, that is, whatever the ref is pointing to or referring to, we wish to gain access to that object. This is referred to as dereferencing the ref. Dereferencing a dangling ref yields a null object because it's not pointing to anything. Oracle Database provides a couple ways of doing a deref. There's implicit dereferencing when we use SQL, but there's also another operator called deref, and this allows explicit dereferencing. We'll provide examples of both. The value operator allows the value or contents of an object to be retrieved. Let's take a look at creating an object type. Here we have an example which has structure, that is, attributes, but no behavior. There are no methods. Create type address as object, and then we define the individual attributes. In this case, they're all built-in data types. What does an instance of this object look like? Well, it would have 4 attributes, making it look like a row in a relational table. There's a street attribute, a city, state, and zip code attributes. Now, consider an object table, or type table as it's referred to in the ANSI SQL standard. This would be a table of these objects. So assuming that we have an existing object type, such as address, we can create a table that will store instances of that type. That is, a table that stores objects. How do we create the object table? We say create table, give it a name, of, and then we refer to the object type. Each row in the table will be an object, a row object, of the address type. This table would have a structure like this. We can describe the table just as we can describe any relational table. So using the SQL+ describe command, we describe addresses, and it tells us we have these various attributes or columns. Although the create table statement is used to create an object table, there is a difference in the syntax from that used to create the conventional relational table. We say it's a table of, and we refer to the object type. So instead of specifying a name and data type for each column of this table, we specify only the name of the object type. The system will use the metadata for this type to complete the definition of the structure of the table. While the structure appears very closely like that of a relational table, this is actually an object table. In an object table, each row represents an instance of that object type. Each row represents an object. What we've been talking about up to this point has been identity and the idea of an object identifier. That is what is different about this table. Each row has associated with it an OID. Because we're working with a hybrid system, an object-relational system, the object stored in an object table can be accessed through an SQL query against the table. Looks like we're accessing a regular relational table. Select asterisk from addresses. And the result will be a bunch of rows presented to us that looks very much like we had just queried a relational table. Thus, we see that an object table is logically and physically similar to a relational table whose column types correspond to the top-level attributes of the object type stored in the object table. But the key difference between a conventional relational table and an object table is that an object table can optionally contain an additional object identifier column and index. The object identifier allows the corresponding row object to be referred to from other objects or from relational tables. So a built-in data type called ref that we've discussed represents such references. So refs use the OIDs to point to row objects. So now with that framework in place, an object type exists. A typed table or object table has been defined to hold these objects. We could now create a relational table with references to the object type. The ref type modifier, or the ref operator, is used to identify the object type which will be referenced by this relational table's column. Here, the column is referred to as home address. It stores references to address objects. It does not store the actual objects themselves. Those are going to be stored elsewhere in an object table. What this means is that instances of the object type can be shared. To accomplish this sharing, we've created this object table with each object to be shared stored as a row object. This new relational table called employee2 has a column that will hold references or pointers to the row objects. And it will be possible to have more than one row in the employee table referencing the same address object in the object table. If we examine the structure of employee2, what we see is the data type for home address indicates that it is a reference. It's a ref. But specifically, what does it refer to? It's a reference to an address object. We've created a table called addresses, which is a collection of objects. Each of these objects represents an address. In our situation, each object potentially could be the home address of an employee. First, let's create some address objects. We insert into addresses the result of invoking the address constructor, address being the object type, and we provide 4 attributes. We insert another row. I create another object. Finally, we can examine the content of addresses, and when we run a query against addresses, the result looks like 4 rows in a relational table, but in reality, we have 4 object instances, 4 address objects. When we insert a row into employee 2, we'll need 3 values. One value will be the employee number, which is numeric. Another value will be the name of the employee, a character string, and the third will represent the home address. Actually, it will be a reference to an address object, a pointer to an address. The address objects that we just placed within the addresses object table will be referenced by the home address column. We'll use the ref operator to obtain a reference to an object when we construct the value that we're going to place in the home address column. We'll insert into the employee 2 table a number. 333 would be the employee number that we're constructing. The name of this employee is Curly. And finally, we need to obtain a reference to an address object. This is accomplished by running a subquery. We select from the addresses table, using this correlation variable that we've chosen, A, pass that as an argument to the ref modifier or the ref function. Specifically, we are looking for the reference to the address that has a street value of Main Street and a zip code of 06120. So the subquery is used in this insert statement to extract the ref, which is then placed in the home address column. Similarly, we could accomplish this objective by using SQL embedded within a PL/SQL program. Once we've defined the address object type, that address object type can be used to define variables within PL SQL. We can use it not only to define data types of a column or the structure of a row, but as soon as we've created the type, it's available universally through the Oracle database. We select the reference for the address object residing in the addresses table that has an attribute value of Main Street for street and 06120 for zip code. We then use the value that we've obtained and insert that as the third column, the home address value. The actual format of the ref may change from version to version, or it may actually be different depending upon how many objects have been instantiated in your database. But the general idea is presented here as to what a ref would look like. So when we place a value in home address for these rows 111 and 222 in the employee 2 table, because all of the rows in the employee 2 table have the same home address, have the same reference, we're going to see that same value appearing in all of them. We can select from the employee 2 table. We can retrieve emp number and name from this table as we would from any relational table. However, because home address is a reference to an object, we're going to use a correlation variable to grab hold of the home address column, hence of the ref, and then construct a path expression and drill into the address object and get the street attribute and get the city attribute. And when we run this query, we get the following information showing that Mo, Larry, and Curly all reside at the same location, the same street address, and the same city. We also can perform data manipulation operations, so we can change an attribute of the referenced object stored in the addresses table. What this will do is any row within the employee2 table that makes a reference to the object in the addresses table that we've updated, we'll pick up that change when we create a path expression from the employee2 table home address to that object. Here we're updating the addresses object table, setting the value of street to Windsor Street, where the street currently is Main Street and the zip code is 06120. When we retrieve our data from the addresses table, we note that the first address shown here is the one that has been modified. Subsequently, when we go to retrieve from the employee2 table, we'll now see a different value for the street for our employees who reside at that address. To change the address of an employee, we must change the ref value for that employee. First, we obtain the ref to the desired address. Then we take that ref and use that as the new value for the home address column. After executing this code, the home address reference now points to a different address object in the addresses table. We confirm this by running a query against the employee2 table. Observe that Mo, employee number 222, now resides on County Road in Wethersfield. Previously, he had resided with both Larry and Curly on Windsor Street in Hartford. So now there are different ref values for these rows. A ref value can be updated directly through SQL. We aren't required to use PLSQL to perform the update. In this case, we're performing the update entirely with SQL. We're updating the employee2 table, setting the home address equal to a ref value. We obtained the ref value by performing a subquery. We apply this only to the home address column for employee number 222. So the ref values for the rows are again the same because what we've just done is we've moved Mo back to Windsor Street. The idea of this query was simply to demonstrate that we could do the update entirely with SQL. The ref operator returns a pointer or a reference to an object. It does not return the object itself. The deref operator uses a ref as its argument, and this operator returns the target of that reference rather than a pointer to the target. So we take home address, which contains a ref to an address object. We pass that ref as an argument to deref, and deref returns the entire object. The value function takes as its argument a correlation variable or table alias for an object table and returns object instances corresponding to rows within that table. The value function is said to return the value of an object. This value is the object itself, intact. This value can be assigned to a variable declared of the object type, and the object can be operated on using this variable in path expressions to invoke methods of the object type. Examining the output of the value operator compared with the output of the deref operator, we see no difference. And that's correct. The two functions produce the same output. The difference between deref and value is not the output. They produce the same result. The difference is the argument that's passed to these two functions. Value accepts a table alias or correlation variable. Therefore, it's constrained to operate on a particular table. Deref accepts a reference to an object. It can follow that reference to wherever the row resides, which could be in a different table. Here's a little example of the value operator in action. We select the value from the addresses table using the correlation variable of A. This returns the object. We place that object into this working storage variable, which has been declared as a variable of the address object type. Once the retrieval completes, we then use the address variable to formulate a path expression and extract the value of the street member variable. Let's compare the difference between the deref and the value operators. First, we create a table of address objects. We'll use this new table called more addresses to discuss the difference between the two functions. What we wish to do is store addresses in two different tables. We already have the addresses table. Now we're creating more addresses. We insert into more addresses a clearly different address than any of those we previously stored in the other table. For purposes of our discussion, all of our employees will be recorded in the same table, employee 2. We'll have the home address column as a reference to address objects. Some of the rows will reference addresses in the addresses table, others in the more addresses table. Here we add the employee Shemp, and his home address is in a different table from Mo, Larry, and Curly. With this PL/SQL program, we demonstrate the difference between the value function or operator and the deref function or operator. We use the value function to extract address objects from the addresses table. Hence, value takes as an argument a correlation variable that we've associated with the addresses table. The address that we placed in more addresses, the home address for Shemp, cannot be accessed through this query. We would have to change the from clause to identify a different table. The deref operator accepts home address, which is a reference column. It's a reference to an address. Note that we're populating that with a reference taken from the employee 2 table. It does not matter which employee we access, whether we're accessing an employee whose home address is recorded in addresses or more addresses. We're simply getting a pointer, a logical pointer or reference. Finally, because the focus of this video pertains to object identity, let's consider what would happen if a new object was created that had the same attribute values as an existing object. All of the attributes had the same exact value of an already existing object. We insert into addresses an object with the values of Windsor Street, Hartford, and so on. This matches the same values for an already existing object in the addresses table. What happens is two different objects now exist. We can distinguish between them based upon the object identifier values, not the object attribute values. These different objects have the same values for all attributes. Now consider the result for each of the following queries. If we select distinct street, city, state, zip code values from addresses, what would we get? Well, we're treating it more like a relational table, so we would not have duplicate rows. In the case of the street, city, state, and zip code being the same, we would have only one row. In the second case, because we're looking for distinct references, there are two different references for these two rows. So we would have two rows in the result of the second query and only one row in the result of the first query for the objects that pertain to Windsor Street. So from an object-oriented perspective, there are no duplicate rows, but from a relational perspective, which is what the first query addresses, there are duplicate tuples in the relation, and we remove those tuples at the request of the distinct keyword. Therefore, what we see is that keys are still needed to provide identification for real-world entities of the application domain. And finally, a little insight to what's going on with the Oracle Object-Relational database with respect to the object identifiers. Although the OID is hidden and not intended to be accessed by users, it is possible to gain access to this kind of indirectly. In normal operation, we would not see the OID. It's hidden effectively to discourage access to it. However, we can obtain access through a pair of pseudo columns that are associated with a table of objects. sys NC OID $sign returns the OID of each row object. sys NC row info $sign returns a description of the constructor method for the row object. And these final brief examples illustrate how these pseudo columns could be used within a query against an object table and show you what the result would be. Hopefully you found this video to be useful and informative. If you're interested in obtaining information about additional videos when we put them out, consider subscribing to the channel. And once again, thanks for watching.